Today we are going to make a revision for what you want, and then we can, of course, solve. I had prepared a sheet that I sent you before. We can solve it together. And if you have any questions, please ask me. So for the hydrogen-oxygen fuel cell that Mohammed asked me to revise with you, it comes a lot in exams. Many exams, they ask about the hydrogen-oxygen fuel cell. And we know that we have two types of hydrogen-oxygen fuel cells. We have what we call acidic hydrogen-oxygen fuel cell, and we have an alkaline hydrogen-oxygen fuel cell. Hello, Yanajud.
Hello, Miss كيفك؟
How are you? Are you fine? Alhamdulillah. Okay. So as I said that many exams have this question about the hydrogen-oxygen fuel cell. And as I told you, there are two types of hydrogen-oxygen fuel cells. These are acidic hydrogen-oxygen fuel cells and alkaline hydrogen-oxygen fuel cells. Now, for the acidic hydrogen-oxygen fuel cells, we have our two fuels are the hydrogen and the oxygen. And inside here, there is an acidic electrolyte, an acidic solution. It means an acid. And of course, we have here two electrodes. I'm just, okay. So we have two electrodes. I allowed you recording. So there are two electrodes here. These electrodes are made of platinum, and they are connected, of course, by wires so that the circuit be closed. And at the anode, we call the place where the hydrogen enters, we call it the anode. And where the place of oxygen entering, we call it the cathode. And as we know that in fuel cells, usually the anode produces the electrons and the cathode gains the electrons. So electrons should come out from the anode and go through the electric wires towards the cathode. Here, when hydrogen enters at the negative electrode, the anode here is the negative electrode because electrons come out of it. So we call it the negative electrode, where electrons are formed. So the anode here is the negative electrode. So we will see that at the anode or the negative electrode, the hydrogen gas at the platinum electrode will ionize to form hydrogen ions plus 2 electrons. And these 2 electrons pass through the wires to go to the cathode, which is the positive electrode, which gains the electrons. We call it the positive electrode. And so at the positive electrode, the oxygen, which is the second fuel, will react with the products of the first reaction happening at the anode, where the oxygen will react with the hydrogen and 2 electrons to form water, and water comes out from here. And so the overall equation will be that hydrogen reacts with half oxygen to produce water only, because the hydrogen ions will cancel with the hydrogen ions and the electrons will cancel with the electrons because they are at different sides. And so the overall equation will be that hydrogen reacts with oxygen to form water. So as we said before, that this fuel cell is very important because it does not produce any pollutants. The only product here is water. And of course, we said that the people, especially astronauts, and sometimes in airways, they usually use this fuel cell to produce water. And at the same time, the electrons that passes through the circuit can produce current. So we can light up a lamp or work a small motor or whatever. And at the same time, we can get water. That's why astronauts use it a lot. So this type of cell, of fuel cell, does not produce any pollution. Now, sometimes we have inside the cell, instead of having an acid, we can have an alkali, like sodium hydroxide, for example. And in that case, also water is going to be produced by the reaction of hydrogen and oxygen, but the method of working differs a little bit. Also here we have hydrogen and oxygen as our fuels, but when the hydrogen enters here and there is an electrolyte, we will see that the hydrogen gas reacts with the OH ion to form 2 water molecules plus 2 electrons. The same, the electrons produced will flow through the circuit and go to the cathode, and there the oxygen will take one of the water molecules and the electrons to form 2 hydroxide ions. And so the hydroxide that reacted at the beginning with hydrogen are going to be replaced once more by the hydroxide that are going to be produced at the cathode. And also water will be produced, but as you see, water is going to be produced in this side of the hydrogen coming in. Water comes out from here. One of the water molecules come out from here, and the other will react with the oxygen and the electrons to form the hydroxide ion that is going to replace the hydroxide ion that was used by the hydrogen gas. And this means that this cell replaces itself, because as OH ions are used up, then they are going to be replaced at the other electrode. Sometimes instead of using hydrogen, they are going to use methanol instead of hydrogen. And so we will see, of course, we don't have to know about the methanol, but in many times they bring it in exams, as we are going to see if we are going to solve the sheet that I prepared for you. We will see that sometimes they use methanol instead of hydrogen. So methanol can also be used instead of hydrogen, but the other electrode must contain oxygen. So only the hydrogen is replaced by methanol, and methanol will produce electrons where it reacts with, for example, it will react with hydroxide ions. If the electrolyte here is an alkali, it will react with the hydroxide ions, producing, it reacts with 6 hydroxide ions, produces carbon dioxide and produces water, and it produces 6 electrons as well, where every hydroxide ion will leave an electron. And here we have 6 and 4 hydrogens. So here we will get 5 water molecules. Here we have 4 and 6 makes 10. So 5 water molecules. So is it balanced like that? I think it's balanced. 5 oxygens plus 2 makes 7 oxygens. They are balanced. Okay, and we get the 6 electrons, and the electrons goes to the cathode, the positive electrode, where the oxygen will take part of the water, also not all of it, because in alkaline solution it takes part of the water and leaves the other part, and together with the oxygen and the electrons and part of the water, it will replace the hydroxide ion that was used before. Okay, so this is all about the hydrogen oxygen fuel cells, because I was asked to revise it with you. And also it comes, I've seen it in many of the exam papers, it comes, I don't have to say a lot, but it comes many times in exams. Of course, as we said, that there are advantages of the hydrogen oxygen fuel cells. They provide, of course, alternative fuels instead of using the fossil fuels that we don't have to use because they are non-renewable. Then we can use the hydrogen oxygen fuel cell as an alternative production of energy. As we said here, that the only product produced is water, so they do not produce the carbon dioxide produced by fossil fuels or the sulfur dioxide that is also produced by burning of fossil fuels. They only produce water, which is, of course, it's not a pollutant at all, but the carbon dioxide produced from the fossil fuels causes the global warming due to the greenhouse effect, and the sulfur dioxide produced causes acid rain, as we usually study. They are lighter and more efficient than engines that use fossil fuels. Of course, there are some problems associated with the hydrogen oxygen fuel cells. That's because of the hydrogen. What is the difference between them? You mean in work or in what? What do you mean by what is the difference between the alkaline and acidic fuel? I just explained the type of work in efficiency. Okay. Now, this was a question in an exam. They said, yes, yes. There was a question here that says that which one of them is more efficient? It's the alkaline. It's the alkaline fuel cell is the more efficient than the acidic fuel cell. Now, why is this? Why the alkaline is more efficient than the acidic? Both are efficient, but the alkaline is somewhat more efficient than the acidic. And this is why, this is because if the acidic conditions are used, it means that we have an acid here as an electrolyte. We use the platinum as electrodes. In both electrodes, we use platinum as the electrode because, as we know, that platinum is inert and it will not react with anything, and so we can use platinum. But in case of the alkaline fuel cell, the oxygen reacts more easily with the hydroxide ions than it reacts with the oxygen. When it reacts with in presence of the hydroxide ion, we will see that the reaction is more feasible. The reaction is more easier when we have hydroxide ions. When we have hydroxide ions, the hydrogen reacts with the hydroxide ions more easily than when it is only going to be ionized into hydrogen ions and electrons. But here, when the hydrogen reacts with the hydroxide ions, this is more easier to react. And in that case, instead of using platinum, which, as we know, is an expensive material or an expensive metal to be used, we can use other metals as well. We can use the iron, we can use cobalt, we can use other metals as electrodes instead of using the platinum. So that's why they say that the type of catalyst used, affects the efficiency, because we know that efficiency depends on how much energy is produced with smaller costs. So here, if you use the alkaline solution as an electrolyte, then we can use the electrodes instead of platinum. We can use other electrodes that are cheaper than platinum, and so the cost will not be so high as in case of using the acid electrolyte, and that's why it's more efficient. Okay, Muhammad? Okay, you're welcome. Do you have any question here? Of course, we know that hydrogen is not easy to work with. Hydrogen as a fuel is not an easy fuel to be used with. Why? Because hydrogen is a gas, and this means that we have to compress it in order to use it as a fuel. We have to compress it, and of course, compressing the hydrogen gas is a little bit dangerous, because as we know that hydrogen gas is flammable, and it can explode if it is subjected to any accident. So when we compress the gas, this is not something that is safe, because hydrogen is a flammable gas. So scientists tried other methods in order to use the hydrogen as a gas. So they used adsorbing of this hydrogen onto the surface of suitable solid materials. Adsorbing means that they used surface of certain solid materials so that the hydrogen will be adsorbed on its surface. But of course, when we use surfaces at which hydrogen is adsorbed, it needs to be heated so as to leave the surface of this solid material. And as we know that heating the hydrogen is not something that is safe. So they tried absorbing hydrogen into suitable materials, and nowadays they are trying nano tubes, carbon nanotubes, in order to absorb the hydrogen and they can use metal hydrides to absorb the hydrogen. But up till now, hydrogen is a problem. It's not something, it's not very simple to use the hydrogen oxygen fuel cells due to the flammability of the hydrogen. Okay. You have any question about hydrogen oxygen fuel cells? طيب okay, what other يعني if you have any problem or any question you'd like me to solve for you or to explain for you, please ask now if you have anything. Of course, I prepared a sheet, but I want you, and if you have any question, you can ask today, inshallah. How does the splitting of the d orbital allows the transition metal produce color? Type, okay. Type, we know that if you get any transition metal compound or complex and you place it in front of light, we know that light, of course, contains many colors, as we have seen before. Of course, the visible light consists of different lights with different energies and different frequencies. And so the substance, the inorganic complex or the inorganic compound, of course, the transition metal compounds absorb the absorbed part of this light, and the other part is transmitted. So light is absorbed by the transition metal compound. Not all of it is going to be absorbed, but part of it is absorbed and the other part of is transmitted. And we see this transmitted, we see the color of this transmitted light. Okay, so we don't see the absorbed, but we see the transmitted, or we say the complementary color. We see the complementary color. Now, what happens when the ligands, for example, when you take something like copper H2O6 plus 2, we say that this has a blue color. Why does it have a blue color? This is, for example, copper sulfate, because of course we don't have something called hexaaqua copper only ion. It should be in the form of a compound. So for example, sulfate, we see that the color of this copper sulfate is blue, isn't it? So why do we see it as colored? Hello, ya Muhammad. Why do we see it as a blue color? And why do we see, for example, copper Cl4 -2 as yellow? This is blue and this is yellow. And we see other compounds, of course, everyone, as we've seen, has a different color than the other. Now, what happens as these ligands approach from the transition metal ion? We know that in the transition metal ions, they fill their electrons in the d subshell, because they fill first in the 4s by 2 electrons, and then they start to fill the 3d subshell. But when they form the ions, the electrons are going to be removed from the 4s, and only electrons in the 3d subshell are going to be present. They are going to be present in the 3d subshell, and we know that the 3d subshell consists of 5 d orbitals. Now, what happens as this ligand or that ligand, or for example, ammonia ligand, approaches the metal ion? What happens to these 3d subshells? They are going to be splitted into 2 higher energy level and 3 lower energy levels. So this splitting happens as any ligand approach from the transition metal ion. We will see that the 3d subshell is going to be split into a lower energy shell, or 3d lower energies, and 2d higher energies with higher energies. We call this the ground state. We can call it, yani, if you don't have to say ground state, you can say the lower energy, the lower energy level. You can call this the lower energy level, and this is the excited state, or we can say the higher. This is called the excited state, or we can call it the higher energy level. Okay, now what happens if we have an electron here present in this ground state or in this lower energy level, and now we subjected the complex, as we did here, to light? So what happens when this light is bombarded, or this electron is subjected to the light? So when this electron is subjected to light, it will absorb the light energy, and it's going to be transmitted, or it's going to be promoted, or it's going to be excited. We can say any word of this. This electron, when it absorbs light energy, it will be transmitted or it will be excited or promoted to the higher energy shell. And on doing so, it absorbed light with specific frequency. And what are we going to see? We are going to see the transmitted light, or we see what we call the complementary color. We see the complementary color. So the electron absorbs a certain frequency of light, and it is promoted or excited to the higher energy level. And when it did so, we saw the transmitted light or the complementary color that this electron absorbed. So why did it absorb this frequency of light? We know that as we know from before that in case of the visible light, we have different, of course, colors. As we know that the visible light is the region in between. It is the region in between the infrared and the ultraviolet. This is the visible light where we can see the colors only. We cannot see colors in any other part. And so the one that is near to the infrared is going to be red. And then we have orange, and then we have yellow, we have green, we have blue, we have indigo, and then we have violet. So the one that is next to the ultraviolet is violet, and the one that is next to the infrared is red. So we have different frequencies, because as we go from the red color to the violet color, the frequency increases, the frequency and energy increases. So some of the ligands will cause the complex to have, for example, a green color. Others will cause the complex to have a red color or to have a pink color. Or so why do the colors change? Why do different transition metals change their colors? This depends on more than one factor, but the main point that we are going to talk about first, it depends on the difference in energy. We call this the gap energy, or the gap between the lower energy level and the higher energy level, or the difference in energy. We can say the difference in energy between the lower energy level and the higher energy level. Depending on this difference, the electron is going to absorb the light, because if the difference or the energy gap here between the ground state and the excited state is small, this means that the electrons need only a small amount of energy, of light energy, a small energy or a small frequency of light in order to be promoted or excited from the ground state to the excited state. But if the energy gap is bigger, so I'm going to draw two drawings here to compare between them. So either here we have a small difference between the two energy levels, or we have a big difference between these two energy levels. So if the electron is present here, it only needs a small amount of energy in order to be promoted from the ground state to the excited state. But if in a different complex, the electron is present here and it's going to absorb the light energy, then it requires a bigger amount of energy in order to be promoted or excited from the ground state to the excited state. So if it absorbs here a small amount of energy, for example, if it absorbs the red color, it will appear blue, because we have what we call the color wheel. We have what we call the color wheel, and the color wheel is divided into the colors that we are having here. So here we have red, we have orange, we have yellow, we have green, we have blue, and we have violet. And so if the energy difference here, or the energy gap, was small, then this electron requires only a small amount of energy to be promoted from the ground state to the excited state. So maybe it will absorb the red color, and if it absorbs the red color, our complex will appear either green or blue, or maybe we call it a cyan. It's in between the blue and the green colors. So it depends on the complementary color. Complementary means the color that that is in front in the color wheel of the color that it absorbed. But if here, for example, the electron, in order to be promoted from the ground state to the excited state, it requires a big amount of energy. For example, it absorbs in the violet region. The frequency, because as we go in this way to the left-hand side, the frequency increases. It means that the energy of the violet light is greater than the energy of the red color. And so the violet, if it is absorbed, then the complex will appear, for example, yellow. If it absorbs the blue, for example, it will appear orange. Or if it absorbs the green, it will appear red. So it depends on the energy gap. And what causes this energy gap? What causes the splitting in some of the complexes to be small, and at other times the splitting is very high or medium high? It depends on more than one factor. It depends on the ligand itself. The difference in energy depends on the ligand. Some ligands are strong ligands, and as they are strong ligands, they're splitting, they will split the D subshell of the metal complex, of the metal ion, sorry. It will split it in a big difference. There will be a big difference or big energy gap between the lower energy level and the higher energy level. And other ligands, we call them weak ligands. This difference will be only small. So this is a factor affecting the splitting. And the other factor that we study is the charge on the metal ion. Charge on the metal ion. Sometimes if the metal ion has a +2 charge, it differs than if it has a +3 charge. Also the splitting differs. The more the charge, the bigger will be the difference. Of course, also the colors depend on whether our complex is octahedral or tetrahedral, but yeah, we don't study this, because in case of tetrahedral, the splitting is completely the opposite of the octahedral. But of course, I'm not going to discuss this because this is not in your syllabus. So we have two factors affecting. We have the type of ligand used, and we have the charge on the metal ion. Okay, so whenever they ask you about the color, all you have to say is that when the ligand approaches the metal ion, then it causes splitting for the d orbitals. Sometimes we start at once, we say splitting of the d orbitals takes place as the ligand approaches the metal ion, and then the electrons in the lower energy shell will absorb a certain light with a certain frequency or with a certain energy, and is going to be promoted from the lower energy level to the higher energy level. And on doing so, the transmitted light or the complementary color is seen. Okay, that's all what you have to say. Okay, why when we add excess ammonia to iron H2O6 +2, nothing will happen? Like, why the ligand exchange does not take place? You said here that when ammonia is added, when we add excess ammonia to the iron +2, nothing will happen. Like, you mean that when we add ammonia, it's like when we add sodium hydroxide? When we add ammonia, is like when we add sodium hydroxide. It forms at the beginning the metal hydroxide, and then if we add excess, no ligand exchange takes place. Okay, it depends on the metal ion itself, yani whether the metal ion will accept to exchange the ligand or not. Yani sometimes, as you have seen, for example, in case of copper, it only when ligand exchange takes place with ammonia, only 4 ammonia molecules are replaced by replaces 4 water molecules. But in other metal ions, it takes 6. It depends on the type of the metal itself, whether it will accept something like that to happen or not. So in case of iron, iron is going to be oxidized at once, and if it's left in the air, it can be oxidized at once to the iron +3. Okay. Okay, thank you so much. Thank you, Amina. Thank you, Sama. So what other questions do you have? if you have more questions. Would you like me to explain anything for you? You want to revise anything? Any part in the syllabus? Type, okay. If you remember anything while we are working, just ask me, please. Type, let's see now. I prepared the sheet that I sent you. I don't know if you have looked at it or you didn't have time to. I just gathered, of course, maybe we have solved some questions of these, but just to remind you of more than one idea. Type, here it says the series below show the first 4 ionization energies of different elements, which could be those of a transition element. I don't know if you solved it or not yet. Yes, excellent, Amina. Maybe I'm not going to wait for all of you because we want to discuss as many questions as possible. Okay, Amina, okay, I will leave 2 minutes for you, okay, to think about it. Yes, Yabisan, excellent. Okay, Yasama. Yes, excellent, Amina. Yes, excellent. What about the others? Sarah, excellent. Okay, Yasama. I'm going to explain it now. Najud, Muhammad, Miss. Okay, Najud. Muhammad. Okay, Muhammad. Muhammad Ahmad ومس. Do you have any answer here? Type. Okay, I'm going to explain it. The answer here is C. Why is it C? Because we know that ionization energies means it's the energy required to remove an electron, and we have, of course, studied ionization energies in AS, and also we've studied it in the transition metal chapter. We said that in case of transition metals, we have the 3D. Usually we fill the argon and then we fill the 4s first and then the 3D. And we said that the 3D and the 4s are 2 energy levels that are overlapping together. So that's why the 4s is filled first by the 2 electrons, and then the D is filled by from 1 to 10 electrons, of course, depending on the metal or the metal itself. But these 2 energy levels are considered as if they are the same energy level. They are considered as if they are 1 energy level because they are overlapping together, which means that when the electrons are removed, of course, they are removed from the 4s first. We remove the first, the second, and then the third is going to be removed from the D. Every time the energy is going to be greater than the previous one, but the difference in energy will not be much. But if you look here at A, you see that there was a jump between the first and the second ionization energies. It was about 500 and it changed to 4,500. It means that there is a big jump that took place between the 500 and the 4,500. There's a difference in 4,000, which means that this element is present in group 1. Now, if we look here at the second one, you will see that there was no difference, or the difference here was only about 1,000 something, 1,300, for example. Between this one and that one, there was also no difference because the difference is about 1,000. It's nothing. But if you look at here between the 2,000 and the 11,000, there is a jump. Between 2,700 and 11,500, then there's a jump. So this means that this element is present in group 3. If we look here, here was no jump. It was only 700 Kelvin. Between this and this, there was a jump. Why there was a jump? Let me draw it here. There was a jump here because it turned from 1,400 to 7,700, about 7,000 kilojoules. Between this and this, there is only 3,000. But between this and this, there is about 6,300 kilojoules. So this is a jump. And we said that in case of transition metals, we do not have jumps between the energies. They are nearly, they are going to increase, as we said, but not by a big jumps. So if you look here between 6,000, about 600, sorry, 60, and 1,300, the difference is about 700. If we look between the 1,300 and the 2,600, it's 1,000. Between 2,600 and 4,000, it's about 2,400 or 500. So the difference, when we have thousands, numbers in thousands, if the difference is 1,000 to 2,000 to 3,000, it's not considered a jump. But here, 6,000 is considered a jump. Okay, so you will see that we don't have a jump between the values. That's why C is the transition metal. Okay, do you have any question? Let's see number 2. A metal M reacts with nitrate in acid conditions. The products are M plus N ions, water, and nitrogen 2 oxide. The reacting ratio of the metal atoms to the nitrate ions is 3:2. What is the value of N in M plus N ion? And we said that this type of questions usually come in exams, usually. So would you please think about it? Okay, Nujud, excellent. Muhammad, excellent. Amina, excellent. Bisan, excellent. Misk, excellent. Sama, excellent. Okay, يا Misk, حاضر. Okay. Sarah, what is your answer? Muhammad Ahmad. Sarah, excellent. Muhammad Ahmad. Muhammad, do you know how to do it, or shall I explain it? Right. Okay. We said that here, they said that the metal reacts with the nitrate ion. So the metal reacted with the nitrate ion to form a metal ion, which we want to know how much is this value, plus water plus NO, isn't it? Now, we are going to start with the nitrate ion. We say that the nitrate ion changed to the NO, and of course, we have to find out the oxidation number of the nitrogen in each. So here we have oxygen with -2, so the nitrogen here has a +2. Here we have 3 oxygens, so 3 times -2 makes -6, which means that the nitrogen is +5, which means that the nitrogen changed from +5 to +2. It means that 3 electrons are gained by the nitrate ion to form the NO. Of course, we can stop here, and we don't have to complete the equation. But if we want to complete it, it's okay. Yani, here we have 3 oxygens and here we have only 1. So here we have to add water in order to balance the number of oxygens. We have to put here 2, and then we have to put here 4H positive. So this is the complete half ionic equation. You understand this part, or shall I repeat anything? Type. Okay. Now we said that here at the end, they said that the reacting ratio of the metal atoms to the nitrate is 3:2. It means that 3 moles of the metals reacted with 2 moles of the nitrate. But here in our half ionic equation, we have only 1 mole of nitrate. That's why this means that this equation is multiplied by 2, so that we get 2 nitrate. From where did I get the 3 and the 2? From the question. It says the reacting ratio of the metal atoms to the nitrate ions is 3:2. It means that 3 moles of metal reacted with 2 moles of the nitrate. So we have to multiply the whole equation by 2. And when we did so, this means that we have 6 electrons type. We know that when the metal, 3 metal, reacts to give the metal ion, which we do not know how much is the charge here. So the number of electrons should be equal, so that when we add these 2 equations, when we add the 2 equations, the electrons must be canceled together. So in the first equation, we have 6 electrons. 3 times 2, we have 6 electrons, which means that also in case of the metal, it must lose the number of electrons that that it will give it to the previous equation. So here we have 6 electrons. So in the second half ionic equation, there also must be 6 electrons, which means that here there should be 2 electrons. Why should we remove here 2 electrons? Because 3 times 2 makes 6, like here 3 times 2 makes 6. So the electrons can cancel, which means that every metal lost 2 electrons to form what? To form the metal M plus 2. When it loses 2 electrons, this means it will have a metal M plus 2. Understand it? Well, do you have any question? And this type of questions comes a lot in exam. So do you understand this, or do you want me to repeat anything? Okay, thank you so much. Now, before we proceed in the sheet, someone asked me to revise the Azodiaz. We have to, yani they want me to revise the Azodiaz. Azodiaz means they are the compounds that contain the azo group. The azo group is the N double bond N. We call this the azo group. Okay. To prepare azodiaz, of course, they are a group of dyes that are used to dye clothes. So we start with the first step is that to prepare what we call the nitrous acid. But as the nitrous acid is very it decomposes so quickly, it's very unstable. That's why we have to prepare the nitrous acid should be prepared. We call it in situ. In situ means during our reaction. We have to prepare it during the reaction, because if we prepare it and leave it at once, it decomposes. It decomposes and forms nitrogen dioxide gas, or it forms nitrogen gas. And so here we have to start with sodium nitrite. We bring the sodium nitrite salt and we add HCl, and in presence of the temperature less than 5 degrees Celsius, or sometimes it's written between 0 and 10, but I prefer to say below 5 degrees Celsius, we get the nitrous acid, and of course we get the sodium chloride as well, but of course we are concerned with the nitrous acid itself. Okay, now this is the first step. We produce the nitrous acid, and then we bring phenylamine. We bring phenylamine, We call this the phenylamine. And we add it to the nitrous acid. And also here, the temperature should be below 5 degrees Celsius, or as I told you, sometimes they write between 0 and 10 degrees Celsius. And in that case, it will produce what we call the benzene diazonium ion. It produces the benzene diazonium ion. You must take care that the benzene diazonium ion must have a positive charge on the nitrogen that is bonded to the phenyl ring, not the other nitrogen. And of course, we can write here benzene diazonium ion. Of course, here also we have to add HCl, because here we have to add HCl so that we know that the phenylamine is insoluble in water. So as the amine group is a basic group, we add HCl so as to form the ammonium chloride ion, which is a salt that can dissolve easily, and we add it to the nitrous acid, and we get the benzene diazonium chloride, and we get water as well. We get the benzene diazonium chloride plus the water. Okay. If the temperature, sometimes they will ask you here, if the temperature exceeds 5 degrees Celsius, or if it exceeds 10 degrees Celsius, we will see that the phenylamine will change to a phenol, and the reaction will not proceed. We will not form azodiaz, but instead phenol is obtained. So the temperature here must be lower than 5 degrees Celsius, otherwise phenol is produced. Now we got this benzene diazonium chloride. So the third step is to react the benzene diazonium chloride we can write only the diazonium ion, yani, as an ionic equation, plus we reacted with, hello, ya Abdullah, I allowed you recording, and then we reacted with phenol or whatever. We reacted with a phenol, but also here we have to add sodium hydroxide for the same reason as we added here the HCl. We said here that the phenylamine is insoluble in water. That's why we add HCl so as to dissolve it to form the benzene ammonium chloride, or the phenyl ammonium chloride salt. Here also the phenol is insoluble in waters. That's why we have to add sodium hydroxide, because the hydrogen here is slightly acidic. So in presence of sodium hydroxide, it will form the ONA salt. That's why it will be soluble. And in that case, the azodide is going to be prepared, which is the N double bond N, which is bonded to the phenol group. Of course, this phenol could be substituted. Yani it could be only a phenol or a substituted phenol. It doesn't matter, whatever they will write you. So here, this means as if this bond is broken, and it's the one that is going to connect the nitrogen to the phenyl, the ring of the phenol ring. Okay, understand it now, or do you have any question? If you have any question, please ask. Okay. Okay, thank you so much. Now we come to the third question in the sheet. Electrophilic substitution mechanisms. Okay, you mean that of benzene, isn't it? The electrophilic substitution mechanisms. Yes, okay. So let's see the electrophilic substitution, electrophilic substitution reactions. No. Okay, electrophilic substitution reactions. Of course, these are reactions containing for the molecules containing benzene ring. So in case of benzene, we say that the benzene, although it contains double bonds, but as the electrons are delocalized inside the benzene ring, then benzene cannot undergo addition reaction except only addition of hydrogen. Maybe you have seen that here, when we add hydrogen under certain conditions, it will produce the cyclohexane under certain conditions only. But all the other reactions of benzene are electrophilic substitution reactions. This is the only reaction that takes place in case of benzene, which is an addition reaction. And it takes place under certain conditions. We didn't study about it, except that when we add hydrogen in presence of platinum or nickel as a catalyst, it produces the cyclohexane. So this is the only addition reaction. But all the others are electrophilic substitution. And this is because, as we said, due to the high electron density, due to the delocalized electrons inside the benzene ring, then this high electron density is going to be attacked by electrophiles. Electrophiles are the species that contain positive ions, and the benzene will undergo what we call electrophilic substitution. Like what? Of course, I'm going to give you examples, and then, so this is the only addition reaction. And as I told you, we are not going to study anything about the mechanism. But for the other electrophilic substitution reactions, the first one is the reaction with nitric acid, concentrated nitric acid plus concentrated sulfuric acid in presence of temperature between 50 to 60 degrees Celsius. We have to know all the conditions and the reacting species, everything we have to know about. And in that case, we get the nitrobenzene as, of course, our product, and a hydrogen is going to be, hydrogen ion is coming out, as we are going to study in the mechanism. But here we produce the nitrobenzene. Now, if we have, for example, benzene reacting with chlorine, for example, or bromine or AX2 in presence of what we call a halogen carrier, which is aluminum chloride, or we can use iron chloride, FeCl3, then we get the chlorobenzene. We get the chlorobenzene, and of course, we get a hydrogen ion as well. So this is a substitution that one of the chlorine atoms substituted a hydrogen, and we get, of course, the hydrogen ion and the chloride ion. And here also we have the hydrogen ion and the hydrogen sulfate ion, as we are going to study in the mechanism. If we react, we have two reactions that we call them Friedel-Crafts. We call them Friedel-Crafts reactions. The Friedel-Crafts alkylation, it means that we are going to add an alkyl group. For example, if I have chloromethane in presence of aluminum chloride or iron chloride, we get the methyl benzene. We call this Friedel-Crafts alkylation, or we have Friedel-Crafts acylation, where an acyl group is added. So if I have, for example, ethanoyl chloride in presence of aluminum chloride, we get the COCH3 group plus, of course, the H positive. Okay, the last one that comes many times, it came many times in exams, that if we react the benzene ring with sulfuric acid in presence of SO3, which we call it fuming sulfuric acid, we call this fuming sulfuric acid containing the SO3, we get what we call benzene sulfonic acid. This is called benzene sulfonic acid. Okay, so these are the reactions of benzene. Of course, I'm going to talk, inshallah, about the reaction of phenols, but now we have the reactions of benzene. Now, what is the mechanism of all these reactions? In all these reactions, the first step should be the production of the electrophile, because these are called electrophilic substitution. Then an electrophile has to be produced, and then the electrophile attacks the benzene ring. So for example, in the first reaction where a nitro group is going to be added, we have concentrated nitric acid in the first step plus concentrated sulfuric acid. And here, since both of them are acids, but sulfuric acid is a stronger acid than nitric acid, then a proton is going from the sulfuric acid to the nitric acid, and it forms H2NO3 positive plus HSO4 minus. And then the H2NO3 positive gives NO2 positive plus water. And this is the electrophile that is going to react with the benzene. So here we have benzene. We draw the delocalized electrons and we get the electrophile. And then always the arrow comes from the electrons towards the positive species. And so we draw an arrow from the electrons, the delocalized electrons of the benzene ring to the nitro group. And we get an intermediate where two of the electrons from inside the benzene ring are going to form a bond between this carbon or any carbon in the ring and the NO2. So here we have a bond between the carbon and NO2. And what caused this bond is two electrons from inside the ring. We had 6 electrons at the beginning. 2 of them are going to form a bond, and the rest, we are going to draw them as, we call this a horseshoe, or what we call it, a semicircle or something like that. Its opening must be in front of the place where the new group is formed. And of course, at the beginning, we had a hydrogen here in the benzene ring. We have hydrogens at each carbon. So this is the intermediate that is formed. And then the bond between the carbon and the hydrogen breaks. And we draw an arrow from the bond between the carbon and the hydrogen. We complete the ring by these 2 electrons are going to go inside the ring, forming the 6 delocalized electrons once more. And the nitro group is obtained, and the hydrogen comes out in the form of H positive. And then the last step is that the hydrogen ion reacts with the HSO4 minus, where the sulfuric acid was acting as a catalyst, and it will return back into H2SO4 once more. And of course, we have water as well from the beginning. So this is the first reaction that takes place. And all the reactions will proceed by the same method, but the only difference will be the first step only. So would you like me to make a revision for all the reactions? Would you like me to go and proceed with all the reactions, the mechanism for all of them? It's okay, Yani. Type. Okay, thank you so much, Najud. Does any one of you need me to type? Okay, Abdullah. Okay, hello, ya Abrar. I allowed you recording. Type. Okay, Abdullah said yes, he wants me to go through the rest of the reactions. So number 2, we have to add a halogen. And so the first step here is that the chlorine or the bromine, whatever we want to add to the benzene ring, reacts with the halogen carrier. We call this a halogen carrier or the catalyst, which is the aluminum chloride. And what causes this reaction to take place is that aluminum is bonded to 3 chlorine atoms, which means that aluminum now has 6 electrons around it. And as any other atom, it wants to have 8 electrons around it to complete the octet. We know what is called the octet rule. The chlorine has to have a complete or a full outer shell number of electrons. So that's why it will take 1 chlorine atom from these 2 chlorines, and it will form the AlCl4 minus plus chlorine positive ion. So this will be the electrophile, and then the benzene will react with the chlorine positive ion. And in the same way, the electrons come from here to the chlorine positive to form as we said, there will be a horseshoe. And here we have a hydrogen, and here we have a chlorine. And then this bond completes the 6 electrons once more, and the chlorine is bonded to the benzene ring plus the H positive. And then at the end, the H positive will react with the AlCl4 minus to return back to aluminium chloride plus HCl once more. Okay. Now for the Friedel-Crafts, Friedel-Crafts acylation, yes, Nujud, do you have any question?
Yes, Miss, for the second reaction, doesn't the nucleophile attack the benzene ring, not the other way around, or am I just confused?
We say that the electrophile attacks the benzene ring, but when we draw the arrow, we draw it from the electrons of the benzene towards the positive charge. Usually the negative, we draw the arrow from the negative because the arrow represents movement of electrons. Is that what you are asking about or what?
Yes, okay. Thank you,
Yes,
Miss.
yes, it's the electrophile that attacks the benzene ring because it is attracted towards its high electron density. But when we draw the arrows, means the arrow shows the movement of electrons. So here, as the chlorine positive approaches the benzene, 2 electrons from inside the benzene will form a bond with the chlorine.
Okay, thank you, Miss.
You're welcome, dear. Now for the acylation and the alkylation, the Friedel-Crafts. So the first step is the formation of the electrophile. So we have, for example, methane plus aluminium chloride. No, it should be methyl chloride, sorry. It should be an methyl chloride plus aluminium chloride also. Here, aluminium wants to complete its octet, so it will take this chlorine away from the methyl group, leaving the methyl group as a CH3 positive, and we have AlCl4 minus, as exactly what happened in case of adding a halogen. And then in the second step, the benzene together with the electrophile, then it will attack the methyl group, forming the intermediate, which is the one having the half circle. We draw a hydrogen and we draw the methyl group. And then the electrons between the carbon and the hydrogen enters the ring. And we get the methyl benzene and H positive. And then in the last step, the H positive together with the AlCl4 minus returns back the catalyst, which is the AlCl3 as it is, and H will react with the Cl. The same will happen with the acyl compounds, but instead of reacting chloromethane, for example, we are going to react the ethanoyl chloride with the aluminium chloride. And so it will form the acyl positive ion. And this acyl positive ion is the one to be attacked with the electrons on the benzene to form here the COCH3 instead of the methyl, and then the hydrogen comes out. Understand, or shall I make it step by step? Abdallah, would you like me to make it in a different step?
No, misunderstand.
Type. Okay. Now for the benzene sulfonic acid, you did not study about its mechanism. You did not study about the mechanism of the benzene sulfonic acid. Okay, so these are the mechanisms that we have to know. Now for the phenols, we said that when we have a phenol, then all these reactions can be done also with phenols, but at mild conditions. All the reactions can occur at mild conditions. And the reason for that, as we said, that the lone pair of electrons on the oxygen are also present in a p orbital. And so these electrons will be delocalized with the 6 pi electrons on the benzene ring. Thus, when these electrons delocalize with the other 6 pi electrons on the benzene ring, they will increase the electron density on the benzene ring, make it more susceptible to be attacked by electrophiles, make it more easier to be attacked by electrophiles. That's why we will see that the conditions will be mild conditions. When the phenol reacts with nitric acid, and when we want to introduce a nitro group to the phenol, it only will react with dilute nitric acid. No sulfuric acid is going to be used. So here, if we have a phenol, it reacts with dilute nitric acid. So very mild conditions to produce the nitro phenol. It produces the nitrophenol. If they say excess of nitric acid, then you add, if they said excess nitric acid, as you see, there is no sulfuric acid, there is no temperature. This is room temperature, very mild conditions. That's because there is a higher electron density on the benzene ring due to these two electrons, the lone pair of electrons on the oxygen. If they said excess nitric acid, then this means that you are going to add 2 or 3 nitro groups to the benzene ring. And as you see that always when we have an OH group, then the entering group enters at the 2, 4, and 6 positions. And this is shown for the test for phenols, for the test of phenols, that when we react the phenol with bromine, we get the 2,4,6 tribromophenol, which is a white precipitate, and this is an indication that our compound is phenol at the beginning. But there is also, the amines do the same reaction. If you have a phenylamine, it will undergo the same reaction with bromine. It will give also a white precipitate, which is a tribromophenylamine. But this test is a special, is a special test for phenols to test for phenols. Okay. Do you have any other question here? Do you have any questions? I just want also to remind you about amines. If we have amines, for example, if we have halogenoalkanes, for example, of course, this is a question inside the sheet that I sent you, but I just want to revise it with you. And if we reacted with ammonia, or if we reacted with amines, we have to use excess of ammonia, for example, to produce the amines, which is the CH3, CH2, and H2, plus we get the HCl. But that's why we add excess of ammonia, because if we do not add excess of ammonia, then something of two things would happen. Here, either one of, if we didn't add here excess of ammonia, so instead of ammonia reacting with the halogenoalkane to produce the amine, part of the ammonia is going to react with the HCl to produce the ammonium chloride salt, which means that the amount of amine produced is going to be a small amount. The yield will be a small yield. Why? Because not all of the ammonia reacted with the halogenoalkane to produce the amine. Part of it reacted with the HCl that is produced and formed the salt that we do not want. That's why here we have to add excess of ammonia, so that part of the ammonia reacts with the halogenoalkane to produce the amine, and the other part of the ammonia reacts with the HCl to produce the ammonium chloride. And so we do not get HCl, but we get the ammonium chloride. But also, since this amine has a lone pair of electrons, then the reaction could proceed, which means that the CH3, CH2Cl would react with the product, which is the CH3, CH2, and H2 here, exactly like when it reacted with ammonia. The lone pair of electrons of the nitrogen would attack the carbon. Of course, we know that the carbon has a partial positive charge and the chlorine has a partial negative charge, the same here. So the nitrogen would attack by its lone pair of electrons, it could attack the partial positive carbon, and we get the CH3, CH2, NH, CH2, CH3, plus HCl. So we get what we call a secondary amine. This is a primary amine. We said that primary amines means that the nitrogen is bonded to a carbon. A secondary amine means that the nitrogen is bonded to 2 carbon atoms. So we get a secondary amine. And the secondary amine can attack the halogenoalkane. This is the, let me write it in a different color. The halogenoalkane could also be attacked by the secondary amine, which is the CH3, CH2, NH, CH2, CH3. It could attack the carbon and produces the tertiary amine. We can write it CH3, CH2, 3N plus HCl. And this also can attack the halogenoalkane. You see that there is a sequence of products. So here also the CH3, CH2, Cl plus the CH3, CH2, 3N. Then this will attack the CH2, CH3, and we get what we call a quaternary salt. CH3, CH2, 4N positive, Cl minus. We call this a quaternary. Quaternary. We call it a quaternary salt. And sometimes they will ask you why a reaction like this will not produce a high yield of the ethylamine. For example, we can start with ethyl, methyl, propyl, whatever. So why do we not get a high yield of this product? We don't get a high yield of this product because the reaction can continue, because we can get secondary, we can get tertiary, we can even get the quaternary salt. The reaction completes, it does not stop. So that's why we do not get a high yield of the amine. Okay, understand this? Well, would you like me to repeat anything? Okay. About the Grignard reagents, do you remember the Grignard reagents? Do you know the Grignard reagents well? You know about them well? Okay, you do not answer. This means that you know them. Let's complete the sheet, or do you have any questions? If you have any questions, please ask me. We can take tomorrow command lesson if you have time. Yeah, we can take tomorrow, but because whenever I ask you if you want to take any more lessons, you do not answer. Yeah. Let's complete the sheet. Here it says use these electrode potentials to answer the following questions. They gave us some of the electrode potentials. I just want to remind you that whenever we have vanadium with high positive charge, then it has an oxygen. Not only the vanadium, any ion that has a high positive ion, it usually comes in the form of oxygen. Like, for example, manganese. For example, when we say MnO4 minus, you see that manganese here has a positive 7. That's why it is bonded to an oxygen. Whereas if we look at Mn plus 2, it's without an oxygen because the charge is only plus 2. So here also, when you see here vanadium, when we have vanadium plus 2, when we have vanadium plus 3, they are alone without an oxygen. But here vanadium is plus 4. It comes with an oxygen. Here vanadium is plus 5. It comes with 2 oxygens. So because I remember that once we were solving a question and they told us what will be the products, and then we wrote vanadium plus 5, and then I told you that if we write vanadium plus 5, this will not be very correct. They will do it, they will give you a mark, but they will not give you the full mark, because when you oxidize the vanadium, for example, from plus 3 to plus 5, we don't have a vanadium plus 5 like this. We have to write it VO2 positive. We have to write it in this form. And of course, we are going to use the equations that are written in the data booklet. So we don't have in the data booklet a V plus 5. We have a VO2 positive. Now, let's look at this question. It says, which of these species is the strongest oxidizing agent? Yes, excellent. Muhammad. Abdullah, excellent. Amina, excellent. Bisan, okay. Sarah, excellent. Miss. Okay, Bisan. Najud, excellent. Which is the most oxidizing agent? Yes, Bisan. Yes, excellent. That's excellent, Bisan. Abrar, where is your answer? Abrar, Muhammad Ahmad. Okay, because I don't want to spend a lot of time. Okay, Abrar. The answer is C. Why is it C? We said that the more the positive is the value of the E naught, this means that the reaction is favorable. The forward reaction is favorable. And we know that oxidizing agents themselves are going to be reduced. The chlorine is an oxidizing agent. It's the strongest of these, not of all the species, but of these, whatever they added here in the table. It's the strongest. Why? Because when it gained electrons, it gave the most positive value of E naught. The most positive value, this means that this reaction is the most favorable, the most favorable forward reaction, which means that the chlorine would like very much to gain the electrons, which means that it's the strongest oxidizing agent because it got reduced. And if you remember that we said that if we arrange the E naught values from the more negative to the more positive, then all the species that are present on the right-hand side are reducing agents. All of them are reducing agents, and all the species that are present on the left-hand side are oxidizing agents. And the oxidizing power increases as we go down the group here, and the reducing power is the most or the strongest when we go up. So the vanadium plus 2 is the strongest reducing agent, and the chlorine is the strongest oxidizing agent. Okay, so chlorine. Now it says which species would convert vanadium 4 to vanadium 3 under standard conditions. I'm going to write the answer here. Which species of these would convert vanadium 4 to vanadium 3 under standard conditions? We want to change vanadium 4 to vanadium 3. Of course, if I write like this, yani it's not vanadium 4 to vanadium 3. Yes, Yabisan, excellent. Najoud. Abrar, excellent. Usama, excellent. Amina, excellent. Muhammad al-Gangihi, excellent. Sarah, excellent. Abdullah, excellent. Misk. Muhammad Ahmad. Type. Okay. So here the answer is vanadium plus 2, which is A. Why is it A? Because they want the vanadium plus 4. This is the vanadium plus 4 because this oxygen is minus 2. This means that the vanadium is plus 4 because when we add plus 4 to minus 2, we get plus 2, isn't it? So they want the vanadium 4 to be changed to vanadium plus 3. They want this equation to be as it is. VO2 positive plus 2H positive plus electron gives vanadium plus 3. They want it like this. So this means that the other one to react with it must be the one to be flipped, because we said that the more positive the E naught value, we will leave the equation as it is, and the less positive is going to be flipped. So we don't have a less positive value than the plus 0.34 except the previous equation, this one. We are going to flip this equation. Why? Because it has a less positive value, whether it is also positive but less positive or a negative. We are going to leave this as it is because they want the vanadium plus 4 to be changed to vanadium plus 3, but we are going to flip another equation. The other equation to be flipped, we don't have except the previous one, the first one. So when it is flipped, vanadium gives vanadium plus 3 plus electron. The electron goes with the electron, and the VO2 positive will react with the V2 positive to change it to 2V plus 3. Okay, and of course, when we add this, we have plus 0.34 volts. And as we flip this equation, then its E naught will also be a positive value. So the addition of these two values is a positive value, which means that, yes, this reaction is feasible. So the answer is vanadium plus 2. Of course, we are in B. The vanadium plus 2 is the A. Oriameski, you have chosen B because you were confused by this. Yani, you understand it now, of course, okay? Any question, please? If you have any question, yani, you should ask now because we don't have time. Our exam is, inshallah, after tomorrow. So everything you want, please ask me now. Type. Let's see. Yes, yes, miss.
We will choose the number less than the original equation.
Yes, you have, because you want this equation to be as it is. مش كده? You want to change the vanadium plus 4 to vanadium plus 3. You want to leave this equation as it is. So the other equation that you have to choose must have a less positive value for the E naught.
Oh, okay. Okay. Got it. Thank you.
You're welcome, Yamas. Let's see number 4. Which of these complex ions could exist as stereoisomers? Abdullah, excellent. Amina, excellent. Muhammad, excellent. Muhammad al-Gangihi. Bisan, excellent. Sama, excellent. Sarah, Abrar. Yes, yes, Sarah. Okay. The answer here is D. Why is it D? Because in stereoisomers, we have either geometric isomers, which are cis-trans, or we have optical isomers. Of course, when we deal with organic compounds, the cis-trans means that we have the C double bond C, and optical means we have a chiral carbon, but these are not organic compounds. These are inorganic complexes, isn't it? So the cis and trans yani, is similar to the cis and trans in organic molecules, but here we have a cobalt bonded to 4 ammonia and 2 chlorine, so both chlorine atoms could be trans to each other, and the rest of the molecules are like this, the rest of the ligands, or else you can draw cobalt, here we have an ammonia, here we have a chlorine, and then an ammonia, and then a chlorine, which is opposite to the ammonia. So this is also a trans. We call this a trans isomer because the chlorine atoms are trans to each other. Or else we have the cis isomer where the cobalt is bonded to both chlorine atoms in a cis position. Remember that we said when we draw the ligands, the nitrogen must be the one that is bonded to the metal ion, not the hydrogen. So here we have these two chlorine atoms are cis. Cis means that they are not opposite to each other, but the trans means that the chlorine atoms are opposite to each other. And we have optical isomers, but not in this example. But we have optical isomers. Optical isomers, we obtain them only if we have a bidentate ligand. If we have a bidentate ligand only. When we have bidentate ligands, we get the optical isomers. But when we have monodentate ligands, we have the cis and trans. Of course, here we have cobalt bonded to 6-ammonia. So there is nothing that is opposite to the other. All the ammonia are similar. So we don't have any stereoisomers. Here we have 5 ammonia and 1 water. The water can be placed anywhere. It doesn't have another water to be exchanged with. Here also we have 5 ammonia and 1 chlorine. But whenever we have 2 chlorines or any 2 different ligands, then they could be present in the cis-trans. Optical means bidentate ligands, like the ethane 1,2-diamine. Okay, 1,2-ethane diamine. Do you have any question before we proceed to number 5? In aqueous solution at pH 12, the amino acid glutamine exists in the form yes, Amina, excellent. Bisan, excellent. Abdullah, excellent. Osama, excellent. Najud, excellent. Sarah Muhammad, excellent. Misk, excellent. Abrar. Abrar Muhammad Ahmad. Muhammad Al-Gangihi, excellent. So the answer here is B, because when we say pH 12, it means an alkaline medium. And of course, we have for any amino acid, we have a basic group and we have an acidic group. So in the alkaline medium, then the carboxylic acid is the one to react. The protons go out because it will be given to the base. And so we get the COO minus, but the NH2 is not going to be affected. But in acidic medium, in presence of an acid, the nitrogen, which has the lone pair of electrons, will gain this proton, and we get the H3N positive, and then we have the CHRCOOH. In acidic medium, the nitrogen, the amine group, is the one to be reacting. In case of an alkaline medium, it's the carboxylic acid that's going to react. Okay, the high resolution proton NMR spectrum of ethyl ethanoate contains Muhammad, excellent. Abrar, excellent. Did anyone was this the answers of the previous question or this question? Amina, excellent. I don't know, is that the answer of Abrar and Muhammad? Yani starting from Amina is excellent. To be said, excellent. But if it's for this question, Abrar, no, you have to think about it once more. Misk, excellent. Okay, I have 2 other answers. Abdullah, excellent. Sarah, excellent. Muhammad Al-Gangihi, excellent. Sama, excellent. No, I'm sorry. Sama, think once more, please. Sorry, Sama. Najud, excellent. Type, okay. Abrar, yes, كده, excellent. So the answer is C, because here this says the high resolution proton NMR. So we are dealing with the protons. Here we have a methyl group where the protons are in the same environment and they are bonded to a C double bond O. This carbon, their neighbor carbon, does not bond to any hydrogens. So these three will appear as a singlet. Now, if we look at these two hydrogens, this is the CH2 that is bonded to a CH3. And this means that if we are talking about these two hydrogens, their neighbor carbon is bonded to 3 hydrogens. And according to the n+1 rule, 3 + 1 makes 4. So these two will appear as a quartet. And on the other hand, these 3 hydrogens are present in the same environment. They are bonded to a carbon. Their neighbor carbon contains 2 hydrogens. According to the n+1 rule, 2 + 1 makes 3. So they will appear as a triplet. Okay. Any question? Type. Let's see number 7. You see here in a methanol fuel cell. That's what I was explaining for you at the beginning of the period of the lesson today. In a methanol fuel cell, in alkaline conditions, the following reaction occurs at one electrode. You see here the methanol plus OH ions gives carbon dioxide plus water plus 6 electrons. The reaction occurring at the other electrode is? Excellent, ya Abdullah. Yes, Sama, excellent. Bisan, excellent. Sarah, excellent. Amina, excellent. Misk, excellent. Najud. Muhammad. Abrar, excellent. What do you think, Muhammad and Muhammad? Yes, Muhammad al-Gangihi, excellent. Sorry, Muhammad al-Gangihi. Yes, ya Najud, excellent. Like Muhammad, you have to think once more. Abrar, you have to think once more. Now, if you look here, I explained this, of course, at the beginning. So here, the reaction is taking place in alkaline conditions. If you choose C, C contains acid, not alkaline. Yes, ya Najud, excellent. It's B. Yes, excellent. It's B. So here, we don't have to choose C because C contains an acid medium. The oxygen is reacting with an acid, although it should react with the products of what happens here is happening at the anode. Why this is happening at the anode? Because electrons are released. We said that at the anode, when we have here, either we write hydrogen or we write methanol. So this happens at the anode. We have here the electrodes, isn't it? And here we have the wires. Here we have, for example, a lamp or whatever. And here is the other cathode. Here, oxygen always comes at the cathode. And at the anode, we have either hydrogen or we have methanol. So here at the anode, oxidation takes place. It means that what is going to enter, whether it is hydrogen or methanol, it will release electrons. So the electrons pass through the circuit and goes to the cathode, where oxygen will react with the electrons that comes from the anode and reacts with part of the water. So oxygen reacts with part of the water and part of the electrons to form the hydroxide ions. Okay. Number 8, cinnamaldehyde is a liquid that is slightly soluble in water, but is much more soluble in ether. It decomposes below its boiling temperature. It can be extracted from cinnamon. Sticks of cinnamon are ground up and mixed with water. Select the correct order of practical techniques to obtain cinnamaldehyde from this mixture. Yes, Abdullah, excellent. Bisan, excellent. Sarah, Amina, Nujud, excellent. Okay, Amina. Muhammad. Sama, excellent. Type. Okay. The answer here is A. Why is it A? Because they said that cinnamaldehyde is slightly soluble in water, but is much more soluble in ether. It decomposes below its boiling temperature. We have taken during our syllabus that whenever we have an organic liquid that decomposes below its boiling temperature, in order to extract it from the reaction mixture, we should make steam distillation. You remember what's the steam distillation? It's when they bring a flask containing water and they heat it, and the steam that comes out from this water, they let it enter to the reaction mixture. Where we have here our reaction mixture. And then here we make distillation. Yani we can do distillation like this. We call this steam distillation. Okay, but of course we don't have yani, this is the steam distillation. So here we get our organic liquid by the steam distillation. Of course, this should be closed. So we pass the steam here, and what happens by the steam? The steam makes what we call agitation to the mixture. It means that both the water and the organic liquid are going to float here at the surface. It comes here at the surface due to the agitation done by the steam. And then the liquid is going to be steam distilled. So we don't want it to reach its boiling temperature. If it reaches the boiling temperature, it will decompose. That's why we do the steam distillation in order to distill it before reaching its boiling temperature. We make steam distillation. So this is the first step to make steam distillation. We don't have to make reflux. When we do reflux if we are going to react two reactants together. But here we do not want to react the cinnamaldehyde with anything. We want to extract it from the water. where we took sticks of cinnamon, grounded them up, and mixed them with water. So the cinnamaldehyde is slightly soluble in water, so it will go to the water, but it doesn't want to be with the water. That's why we have to extract it using ether, because it is much more soluble in ether. So we are not going to make reflux, because refluxing is done whenever we want to react two things together. Even if you are making filtration to get rid of the sticks of cinnamon, if you want to make filtration at the first step, then you have to do steam distillation in the second, not reflux. That's why these two are wrong. Now, if you make steam distillation, why do you want to filter? For those who answered number D, why do you want to make filtration? When you make steam distillation, then whenever you have anything solid will stay in the flask. So you don't have to make any filtration. You have to extract it with ether. You take here, there will be a mixture of the cinnamaldehyde in water, because both the water and the liquid are going to be distilled off of the reaction mixture. So you want to extract it with ether, because it is more soluble in ether, and then distill off the ether. You want to remove the ether by distillation. Okay, you understand why A is the answer? Do you have any question? Yes, Amina, do you have any question? Okay, thank you so much. Right, let's see number B. Which test result for cinnamaldehyde is not correct? I'm going to write you the structure of cinnamaldehyde and see which is not correct. Yes, excellent, Amina. Bisan, excellent. Abdullah. Sarah, excellent. Muhammad, excellent. Muhammad al-Gangihi. Najud. Abrar, excellent. Misk. Abdullah, this is excellent, yes. Sarah answered Sama. Yes, excellent, yes, Sama. Okay. Najud, excellent, yes, excellent. So I think all of you answered. Abrar, did you answer? Yes, Abrar answered. Muhammad Ahmad is the only one that didn't answer. Okay. So of course the answer here is A, because they said which test is not correct. Here we have an aldehyde group, and we know that the aldehyde groups, when we warm it with an acidified potassium dichromate, it will be oxidized to carboxylic acid, which means that the color will change from orange. The potassium dichromate color changes from orange to green, which is the chromium plus 3. But here they said no change. It should change the color from orange to green. So this is not correct. But if we warm it with acidified potassium manganate, we know that the C double bond C, it has two tests. Either we add bromine water, where the color changes from orange to colorless, or we add acidified potassium manganate, the color changes from purple to colorless as well. Because the potassium manganate oxidizes the double bond to an OH here and then OH in the other carbon. So the solution decolorizes. So this is a correct answer. Add phosphorus 5 chloride. The phosphorus 5 chloride reacts only with alcohols and with carboxylic acids, resulting in the formation of misty fumes of HCl. But here we do not have neither an alcohol nor a carboxylic group. So that's why no change takes place. So this is a correct answer. They want not correct. Warm with Tollens reagent. We know that Tollens reagent and Benedict and Fehling, all these react with aldehydes. So with Tollens reagent, it will give a silver mirror. with Benedict or Fehling, it will give a red precipitate. And as we said before, with the potassium dichromate, it will give the green color. Okay, so the answer is A. Number 9, how many isomers containing a benzene ring are there with the molecular formula C6H3NO2O2OH? Okay, Abdullah. Sama? Yes, Abrar, excellent. Amina, excellent. Sama? Bisan, excellent. Najoud? Sama, excellent. Muhammad? Sarah? Okay, Najoud. Muhammad? Okay. Sarah, do you have an answer? Okay, it's C. It's C, Abdullah. Let's do it together. We have a benzene. They said that we have a benzene ring, and we have an OH, and we have two NO2. So both NO2 could be present here beside each other, or an OH where one of them, we keep one of them at its position and we change the position of the other. We have an OH, the NO2 is here, and we change the other NO2 to be here. And here we have an NO2 and also an NO2. So these are 4 isomers where we kept one of the NO2 at position 2 with respect to the OH, and we changed the other. Now we can change the position of this as well. So we have a benzene and on OH. So the NO2 could be here, the first one, instead of being next to the OH, it will change its place, and we have an NO2 here. Or else we keep it in this position and we change the other one with respect to it. So these are the 6 isomers. If you try to put the NO2 here, so both NO2 will be opposite to each other. It's just like this one. It's just like this one. If you put the NO2 here, as if it is the NO2 beside the OH, it will be here, and the other one will be opposite to it. So these will be repeated. If you want to put the NO2 here and the other here, it will be exactly like when we put it here. If you put the NO2, this one here and the other one here is exactly like this one. So it will be a repeated isomer. Yani whenever you try to change the NO2 group with respect to each other, you will get one of the already done. Okay. Any question? Type number 10. What is an organic product of the reaction between ethylamine and chloroethane? This is what I was explaining to you from several minutes. Yes, excellent, ya Abdullah. Amina, excellent. Bisan, excellent. Sama, excellent. Sarah, excellent. Misk, excellent. Okay, yes, the answer is D, as most of you answered, because some of you didn't answer. Yes, yeah, Muhammad, excellent. So the answer is D, and this is what I explained to you at the beginning of the lesson. Okay, number 11, part of the structure of a protein is shown. How many different amino acids were used to form this part of the structure? Yes, Sama, excellent. Muhammad, excellent. Najud, excellent. Amina, excellent. Bisan, yes, excellent. Abdullah, excellent. Sarah, excellent. Abrar, Miss. Type. Okay, so the answer here is B, because whenever we want to know the amino acids, we come between every C double bond O and NH, and we put a line, means that this is an amino acid that differs from this, between the C double bond O and the NH, between the C double bond O and the NH. You see, I'm putting a line between the C double bond O and NH in all. Now, we look at this amino acid. It contains a C double bond O, C, and a methyl. Here we have a C double bond O, C, and a methyl. So these two are similar. This is the first amino acid because we have a C double bond O, C, and the methyl, and then an NH, C double bond C, methyl, and NH. So this is the first one. If we look at this, it's an NH2, CH2, C double bond O. So here also we have this one. No, 1 minute. Okay, let's leave this. Let's take this one. Let's take this one. It's an NH2C and then a methyl. It's similar to this one. So this is 3 and this is 3. They are similar. And this is the fourth one because it is different. So we have 4 different amino acids. Okay. Yani just we want to yani be careful when we compare the structures together. Which organic compound reacts with a greener reagent to give a product that forms a secondary alcohol on hydrolysis? Yes, Abdullah, excellent. Amina, excellent. Bisan, excellent. Sama, excellent. Najud, excellent. Sama, sorry, Sama, excellent. Najud, would you please think once more? Sarah, excellent. Yes, ya Najud, that's excellent. Muhammad, excellent. Yes. Misk, excellent. Bravo. Abrar, did you answer, Abrar? Yes, Abrar answered. Okay, so all of you answered B, which is ethanol, because we said when carbon dioxide reacts with greener reagent, we get the carboxylic group, the carboxylic acid. When methanal reacts with Grignard reagent, we get a primary alcohol. When any aldehyde other than methanal reacts with the Grignard reagent, we get a secondary alcohol. When a ketone reacts with Grignard reagent, we get a tertiary alcohol. This is a ketone. Methanal would produce primary alcohol, but they want a secondary alcohol, so it's ethanol. Excellent all. A compound with the formula C4, C6H14 gives a carbon 13 NMR spectrum with, what's 13? Yes, you didn't write the answer, with 4 peaks. Which compound gives this spectrum? Yes, Abdullah, excellent. Bisan, you wrote 13. Yes, Amina, excellent. Bisan, yes, excellent. Yes, yeah, Bisan, excellent. Sama? Najoud, excellent. Abrar, excellent. Miss Muhammad? Sarah? Sarah, excellent. Muhammad, excellent. So the answer is B, because we want 4 peaks. It means 4 different environments for carbon. So here, these 2 have the same environment. These 2 have the same environment. This has a third environment, and this has a fourth. But here, these 2 have the same environment. These 2 have the same environment, and these 2 have the same environment. So we have 3 peaks, not 4, for A, for those who answered A. For D, these 2 have the same, no, these 4 have the same carbon environment, and these 2 have the same carbon environment. So we have only 2 peaks, not 4. Okay. Do you have time to complete, or shall we stop here, and shall I send you the mark scheme and you do it by yourself if you'd like to? If you have time, we can go through them together. But of course, not only we have multiple choice questions, but I have gathered also some of the, these are multiple choices, and section B contains questions, other questions as well. So would you like me to, either of 2 things, either we meet tomorrow and complete the sheet together, or else I can send you the mark scheme and you solve it by yourself. And please, because as you, yani, more than one of you told me that in unit 4, you didn't have time to complete the paper. As I usually tell you, when you solve past papers, try to solve it in the time given. So you practice how to be quick. You practice how to do all the questions in the time that is given. Yani, many of you told me, not of course those who are studying only unit 5, it's okay, but in unit 4, although they knew the answers, but they couldn't solve the questions because they have no time. They had no time. So please practice that you put the clock in, yani, in front of you, and try to solve the questions in the time required. And the second thing, please start with sections B and C first to collect marks, and then go to section A, because sometimes section A needs thinking, and you think for a question, for example, for 5 or 6 minutes, and it has only 1 mark. But if you solve another question in B or C, you get 4 or 3 marks. So of course, yani, I think it's better that you solve sections B and C first, and then go back to section A. It's better because you will gather or you will collect more marks. That's my opinion, of course. Okay? Or else you start with section A, but if you have a question that you think that it will take time from you, leave it and put a mark to show that you didn't solve this, and then return to it back after you finish all the paper, either this method or that method, so that the time will be okay for you. So what do you want? Please write to me on our page. Either we have a lesson tomorrow at what? From 3 to 5. From 3 to 5, we can have a lesson, or else I will send you the mark scheme today, yeah, and you solve it by.
Miss,
Yes, yeah, Abdul.
can you send us the marking scheme and we solve it, and then any questions that we don't understand, we can do them with you tomorrow in the lesson?
Type, okay. Type, okay. Do you all agree by what Abdullah said? Do you all agree? Type, okay. Halas, okay. Thank you so much. Inshallah, I'm going to send right now, inshallah, the mark scheme. And please, whenever you find any question, please at once, yani send it to me on WhatsApp. Okay, thank you so much, and best of wishes for all of you. Thank you all. Best of wishes and best of luck, inshallah. Same to you, ya Amir. Same to you. Allah yafiki, habibit qalbi. Thank you so much, Miss Bisan. Thank you so much. Same to you, dear Muhammad. Thank you so much. I wish you all A stars, inshallah. Okay, bye-bye. Thank you, Muhammad. Thank you, Bisan.